Hello viewers, in this lecture we will see two examples for inverse kinematic solutions of robot manipulators. So, in the first example we will see a 3 degree of freedom manipulator, and then in the second example we will see a 4 degree of freedom robot manipulator, for which we will construct the kinematics equation and then the inverse kinematic solutions. So, for this first example we see the following robot manipulator. So, we consider a platform in which the axis of rotation is the vertical direction. We call it as the Z0 direction. So, the entire platform rotates in the horizontal plane with the vertical line as the axis of rotation. Then the robot manipulator is placed here, the stem of the robot manipulator is placed here, for which there is a joint which rotates with the axis of rotation perpendicular to the plane of the paper. So, let us say Z1 is the direction which is perpendicular to the plane of the paper. That means Z0 and Z1, they are perpendicular to each other. So, at this position, if we call the point, this point as O and this point as A and this joint as B and this joint as C and another joint which is the end effector D, the final one. So, we assume that there is a rotation about the Z0 axis. So, that angle we call it as theta 1, and there is a rotation about the Z1 axis. So, that we call it as theta 2, and the joint C will move forward and backward, that is a prismatic joint. So, we call that direction as Z2 direction. Then at the end effector we have the approach direction, that is Z3 direction. So, now using the DH procedure we can fix the coordinate frames and then find the parameters of the robot manipulator as given in this table. So, the first thing is Z0 and Z1, they are perpendicular to each other, they do not intersect, and so the shortest distance, if you draw the intersection of the shortest distance line with Z1 axis can be taken as the origin. So, if you take the shortest distance point, the point B is the point of the shortest distance, because Z0 line is like this, Z1 is perpendicular line. So, the shortest distance is intersecting at the point B here. So, that point is called the origin O1 for the second joint. Now, Z1 and Z2, they are also intersecting at the same point B, the direction. So, we can call it as the origin O2 also. So, the origin O1, O2, both of them are at the point B, and the base origin is at the point O here, and another joint is the end effector, that we can call it as O3, that is at the point D. So, now we can fix the x direction, that is Z0 and Z1 do not intersect. So, the shortest distance line itself will give the x direction of the coordinate frame. So, what we can do here is the base coordinate frame, it is O, Z0 is here, and then A, the point B is this distance, the perpendicular direction is Z1. So, here it is O1 and O2. So, the shortest distance line, this line itself will give the x1 axis. Z0 and Z1 are parallel, the shortest distance line, the extension will give the x1 axis. Similarly, Z1 and Z2 are also intersecting here. The line perpendicular to both of them, Z1 and Z2, will give x2 direction, which is perpendicular to both Z2 and Z1 direction. Now, by fixing the point BK, as we have seen, BK is the point of intersection of Zk minus 1 and Xk. And so, by fixing the point B1, B2, B3 etc., we can see that the point dk is distance between OK minus 1 and BK. Similarly, AK is distance between OK and BK. BK is the point of intersection of Zk minus 1 and Xk. So, these rules can be followed and we can easily obtain the values of all the parameters theta, d, alpha and a from this expression. So, we can easily see that the distance OA, this one is A1, the point O to A, this distance is A1 and A to B, that distance is D1, this is OA, and AB is D1. For the second joint, because both the coordinate origins are coinciding here itself, so A2 and D2 both of them are 0, there is no link length or the joint distance, both of them are 0, but there is a joint angle theta 2, there is a revolute angle theta 2 available at this joint B. Then the third one is the prismatic joint, and the point B we can get D3 as B3 and O2. So, O2 is the point B and D3 B3 is the point D. So, the distance B to the end effector BD, this thing BD will give the joint distance for the third joint, and A will be 0, the twist angle is 0 because both the z axis are parallel, then and it is a prismatic joint, therefore there is no angle of rotation, that is 0 here. So, we got the parameters here. Now, by substituting these parametric values in the I minus 1 Ti, the homogeneous transformation for the ith frame with respect to I minus 1th frame, we can easily obtain 0 T1, 1 T2, 2 2 T3 by just substituting from the table values. Then multiplying all these 3 we get 0 T3 to be equal to this expression. So, it gives that the end effector frame, the third coordinate frame with respect to the base frame. Now, if we equate the end effector frame with respect to the base frame to a homogeneous transformation. So, by giving this n x, n y, n z, all this, any the first 3 by 3 matrix is a rotational matrix, and then the fourth column gives the shifting of the origin with respect to the base frame. So, if we give a suitable 4 by 4 homogeneous transformation matrix and equate it with the kinematic expression 0 T3 here, then we can get the inverse kinematic solution very easily. That is, for example, cos theta 1 into cos theta 2 is given by n x, and n y is the sin theta 1 into cos theta 2. Now, dividing both we will get tan theta 1 equal to n y. So, because we know n y by n x, we will get the value of theta 1 by seeing the values of n x and n y. If both of them are positive, then tan inverse of the positive quantity we will get between 0 to pi by 2. The first quadrant if both n x and n y are positive, it falls in the first quadrant. So, the tan theta value will be, so theta value will be between 0 to pi by 2, whatever is coming. If n y is negative and n x is positive in the fourth quadrant, then we will get the angle to be the 360 minus theta, or we can say that minus theta will be the expression. Whatever value we get for tan inverse modulus of n y by n x, then with a minus sign we will get the angle, because that number falls in the fourth. If both of them are negative, n x is negative, n y is also negative, it falls in the third quadrant. So, we will get tan inverse of that value plus pi will be the angle to be obtained. So, depending on n x, n y value and its sign, we will get the exact value of theta 1 from here. And similarly, we will get n z by a z. If you take n z and the a z quantity, this one. So, this will give tan theta 2. From here we can get the value of theta 2 by taking the inverse. Similarly, by equating the various expressions, once we obtain theta 1 and theta 2 from this expression, we can also get the value of d3 by using the simple manipulation of the various terms here. So, this is called the inverse kinematic solution of the problem. So, for a given end effector position, the inverse kinematic solution theta 1, theta 2 and d3 can be obtained like this. So, by making suitable rotation of the actuators using these angles, we will reach the end effector position as given in the T matrix like this 0 T3 expression. So, in this example 2, we will consider a 4 axis robot manipulator which has all 4 revolute joints. So, first let us consider the first stem OA. It is having a revolving axis. OA is the axis of revolution, and we call it as the Z0 axis. Then at the joint A, there is a axis of rotation which will be the perpendicular line to the Z0 axis. So, if OA is on the plane of the paper, then the axis Z1 is perpendicular to the plane of the paper. Then at the joint B, there is a axis of rotation which is parallel to the Z1 axis. So, Z1 and Z2 axis are always parallel to each other, and it will be perpendicular to the plane of the paper at this position. And at the same joint B, there is another axis of rotation which is in the direction of BC. The approach direction itself is the axis of rotation in this particular case. So, we have the joint O, A, B, C, 4 joints are there, and then there are 4 revolving axes at these joints. Now, we can easily fix the various joint parameters theta, d, alpha, a as in the case of the DH parameters. So, if you see that Z0 and Z1 are perpendicular, so the origin O1 is at the point A, and Z1 and Z2 are parallel. So, the line joining, the shortest distance between them is along the line AB. So, the point B is the origin O2, and the point B itself is the origin O3, because Z2 and Z3 both of them are intersecting at the point B, and the Z3 and Z4 they are intersecting at all the points. So, a suitable point is selected, that point is the end effector position C, is called the origin O4. Now, we can fix the x direction. Arbitrarily we can fix the x axis x0 and then corresponding y0 to form a right hand system at the base, and Z0 and Z1 are perpendicular to each other. We get the x1 direction as perpendicular to both Z0 and Z1. So, that is the x1 direction, and Z1 and Z2 are parallel. So, the line AB extension will give the x2 axis. Similarly, Z2 and Z3 they are always perpendicular to each other. The cross product will give the x3 axis, a line perpendicular in this direction, it is x3 axis. And at the end effector, as the convention, we can fix the y direction as the line joining the fingers, and the x direction as the y. Cross z direction will give the x4 direction. So, using this, now we can fix the B1, B2, B3, B4 points as the intersection of, for example, B1 is intersection of Z0 and x1. So, Z0 is this, x1 is this axis. So, the point A is B1 and B2 is Z1 and x2. Z1 is this direction, x2 is, so again B2 is placed at the point A itself, and B3 is Z2 and x3, Z2 and x3. So, this point is B3, the point capital B is B3. So, using that we can measure D1. D1 is distance between O0 and B1. O0 is the O point and B1 is A. So, this is OA, D1 is OA is given, And similarly we can easily see A1 is the distance between O1 and B1. So, here we can see that O1 and B1 are at the same place. So, the A1 value is 0. So, like that we can fix using this rule, fix all the parameters ai, di, theta I and alpha I. Here all the 4 joints are revolute joint, therefore, this theta 1, theta 2, theta 3, theta 4, these are the variables in this system. Now, substituting those values in I minus 1 Ti, we get 0 T1, 1 T2 etc. So, this D1 value is nothing but OA and A2 value is AB, the distance. So, and we can see that D4 value is BC. Now, substituting all these values in the product, we finally obtain the direct kinematic problem, the equation 0 T4 is the end effector position with respect to the base of the manipulator. Now, if we are given a specific 4 by 4 matrix representing the end effector position like this NOAP matrix, then we can directly equate each terms. Here we can easily see that even though there are 12 such equations, there are 12 expressions here and in the right hand side corresponding 12 numbers are there. So, if you equate there are 12 such equations, 12 equations are there, but only 6 of the equations will be independent equation, because for any rigid body the position and orientation will be measured by 6 quantities only. So, only 6 such equations are independent equations. So, using 6 of them we can easily solve the entire equations. We can find the parameters theta 1, theta 2, theta 3, theta 4 can be found out by just equating them. So, for example, R11, the first number is equated with the first value cos theta 1 into cos theta 2 cos theta 3 minus sin theta 2 sin theta 3 into cos theta 4 minus S1 S4 means sin theta 1 sin theta 4, that is R11. Similarly, R21. Now, we can easily obtain from the equation the sin theta 4 is equal to, if you multiply the first equation with S1 and the second equation with C1 and then subtract, we will get sin theta 4 is equal to this expression. Moreover, we can easily get tan theta 4 from R32, this one, R32 divided by R31. We can see from here R32 by R31 will give tan theta 4, from where we can find theta 4 is tan inverse etc. So, depending on the sign of these two, whether it is in the first or whichever is the quadrant, accordingly we will get the value of theta 4 from here. Similarly, we can get theta 1 value from these two expression, the R23 is this expression and divided by R13 is this one. If you divide this two, we will get tan theta 1 expression. From here we will get theta 1 is tan inverse etc. So, once we get theta 1 value from this expression, we will get cos theta 1 into C2 S3 plus C1 from S2 C3 from this equation. This is equal to R13. So, once we obtain theta 1 and theta 4, now from this equation from R13 we can obtain C1 multiplied by C2 S3 plus S2 C3 equal to R13. So, that will give you C2 S3 plus C3 S2 equal to R13 by cos theta 1. So, the right hand side is known. So, we can obtain the left hand side by this number. Now, from the equation here R11 and R21, we get C1 R11 plus S1 R21 is given by C2 C3 minus S2 S3. So, we get for example, we call it as equation 1 and this as equation 2. So, now we can obtain one of the from these two equation and combining with any of this R, that is P1 equation from here and P2 equation P1 and P2, combining these two we can find theta 2 and theta 3 also. So, all the values of thetas theta I can be obtained by just by simple manipulation of these algebraic equations, and finally we get the inverse kinematic solution of the problem. So, the usefulness of the inverse kinematics is, as we already know, that if the end effector position is given, the position and orientation of the end effector is given with respect to the base of the manipulator. By finding this theta 1, theta 2, theta 3, theta 4 and adjusting the actuators according to the solution, we obtain the required end effector position. This procedure will be very useful in controlling the robot manipulator for tracking objects or in the problem of pick and place type of work while a robot is performing such a task. This will come as a very useful tool. Okay. So, those controlling of robot manipulators will be seen in the coming lectures. Thank you.